Swayam Prabha. Digital India. Educated India.
Good morning everybody. In the last class we were looking at how instabilities happen in lean premixed combustors, and we specifically looked at equivalence ratio fluctuations caused by the modulation of the fuel flow rate and air flow rate, and we derived expressions for the heat release fluctuations. We could do this either in time domain or in harmonic domain, and then we also discussed how we can couple it with the acoustic model either in the time domain or in the harmonic domain and do all the analysis. Now a lot of questions were raised towards the end about what the simplicity of the analysis and what all things you are neglecting and so on, but in any case if you do a simple analysis we can see something, but I do agree that more complicated analysis will have to be done, and I will speak about some specific issues which are there in real combustors now, which I did not want to address because if I start addressing that then I would not show the main point. So from the model we developed we saw that the time lag is a very important parameter, and we saw the time lag related to it was predominantly dictated by the travel time of the convective travel time, plus of course the acoustic travel time was much shorter compared to that, but that could also influence it. And so we have a qualitative understanding, and we also have in some sense a quantitative way to calculate the stability and so on, which we did not do that yesterday, but based on the acoustic solver we can calculate the stability quantitatively. Now there are many different mechanisms that affect the heat release rate other than what I discussed. So one is the direct influence of the velocity fluctuations and on the turbulence, and the turbulence will modify the flame speed, and the acoustic oscillations may interact with the turbulent fluctuations and alter these things. Then there are coherent vortices which are shed from the burner exit, that is you can see vortex roll up and so on, and the fuel goes in packets, and it is the fuel flow rate or the mixture is being modulated by this vortices that is shed. And in addition we have this equivalence ratio fluctuations which we already discussed, but these things will come together. So acoustic velocity fluctuations at the flame front will give rise to kinematic perturbations in the position of the flame, so it will lead to perturbation in flame area, hence perturb the heat release. So this can happen even in this kind of combustors, that is we discussed this in a very simple combustor where you had a laminar ducted flame, and we saw how the flame was wrinkled because of acoustic oscillations and how that fluctuated the heat release rate. So there is no reason why that mechanism would not happen in this kind of a combustor. So you can have the acoustic oscillation, you can have this equivalence ratio fluctuations, but on top of that there is wrinkling, and the equivalence ratio fluctuations are also convected, and so therefore the mixture is burning at different place, and there these two things can interact. So that is the first thing. And therefore the perturbation in heat release will be more complicated than what you studied in either of these cases, and people have looked at this kind of situation in the literature. Now the second thing is acoustic waves may give rise to changes in turbulent burning velocity, and even for laminar flames the burning velocity can change, because as I mentioned due to curvature the flame velocity will change, and in turbulent flow of course it will definitely affect. So the reaction rate can perhaps change, and therefore SL can change. And now the third thing is you can have large scale coherent structures, which is the vortices, they roll up, and so they affect the stability in several different ways. One is vortex structures will perturb the flame area, because you have a flame area and the vortex is rolling, the flame will also start going along with it, so it will perturb the flame area. The second thing is it will contribute to perturbations in the turbulent burning velocity. So So one view of turbulence is that turbulence consists of vortices and the large vortices are interacting with the small vortices and so on. So definitely there are a lot of studies which have been done on this, on simple problems, where they show that these vortices can perturb the turbulent burning velocity, and it is necessary to take into account the delay in convection from the origin of the vortex shedding to the location of the heat release rate. So so these things can happen together with this equivalence ratio fluctuations in real combustors, and so things are not as simple as what we did. I completely agree with that, and we will take a look at these mechanisms. Specifically, we will look at this role of vortex shedding in the combustion instability. I think that is what you were kind of alluding to in last class. So I will give you two nice references. We can download them from Science Direct. This is somewhat old, I mean 1992, but it is a very nice reference written by Shadow and Goodmark, titled Combustion Instability Related to Vortex Shading in Dumb Combustors and Their Passive Control, in this journal Progress in Energy and Combustion Sciences, volume 18, page numbers 117 to 132. Must say a word about this journal Progress in Energy and Combustion Sciences. This is a journal which publishes exclusively review articles, and there is no regular paper. It gives only regular articles. So each article gives an overview of the recent development of the subject, so in the last 5 years or 10 years, and it gives a large number of references. For example, some articles give 50 references, some give 100 or 200 references. So if you are starting out in a new subject, the first thing to start off is perhaps look for a review article in the topic, and in combustion these are all published in this journal, and that is a good way to start off with. So this article gives a good overview of the subject. I will give you another reference which is 10 years later approximately, again from the same journal. Oh, I did not write the title. Dynamics of flame vortex interaction. So here the article is focused on how the flame vortex interaction happens, whereas the other one it emphasizes combustion stability itself. So I think please read these articles. So let's so I'm going to discuss qualitatively what happens, because it's not possible to in this context of a class, it's not possible to make a very simple mathematical model. To capture vortex shedding, you have to solve with CFD, and I think that's beyond the scope of the class, but I will just give you some highlights of the phenomena. So I will first draw a schematic or a cartoon of how a flame would look like. So let's say there is a splitter plate here, and you have a fuel coming from this side and oxidizer here, and you would have instability waves like this. So this would probably be the way the vortex sheet would look like, rolling up and so on, and this would be the flame front. And you can also have a situation where you have in the same configuration fresh gases here and burnt products here in the recirculation zone, and you can still have a similar roll up, and definitely the roll up is a periodic phenomena. So naturally anything periodic would mean there is a possibility that that will give rise to fluctuating heat release oscillations, fluctuating heat release rate, which of course if it can be in phase with the acoustic field, the pressure oscillations, then you can of course drive the pressure oscillations. So that is the idea. Now I will redraw this cartoon, zoom in on, let us say, this region, and so this again is fuel, or it can be fresh gases also. I can have oxidizer here, or I can get the same picture when I have or burnt gases, and you have something like a vortex here, and this would be the flame front. So so we can imagine that these kind of situations can arise in a combustor, right? Can you? So the idea is to have a discussion on what role these things play on combustion instability.
There will be symmetric flame front on the other side.
Yeah, this is just I will draw that in a second. So this is just a very simple situation where you have a shear layer with a splitter plate, so like a academic configuration or something, so where they show the vortex roll up. Similarly you can get a flame, and this is just zooming in on this, but in reality yes, I will talk about it in a few minutes. Because in reality you can't have a combustor with just a plate here and so on. We have to have a combustor to have combustion, yes, and so then all those things will be there. Anything else? Okay, so in dumb combustors or combustors with bluff body flame holders, vortices are formed in the shear layer between the high speed and low speed streams, let us say at the rearward facing step or the backward facing step, which is called the dump combustor, or in the wake downstream of the bluff body. Bluff body can be used as a flame holder. So the vortex formation is there, and it is something which you cannot get rid of, but neither can we get rid of this kind of generic combustion configurations, like where the flame is being stabilized by some kind of recirculation zone, because why is this recirculation zone necessary to stabilize the flame? What happens if it is high? Yeah, okay, so the flame, typical flame propagation velocity is laminar flame speed is of the order of less than meter per second, and even in turbulent flow it will be at most few meter per second, and we want to have the combustor working at much higher, have flow at much higher velocities, because then higher the flow rate then you get more heat out of it, so that is the idea. So then we need to somehow make sure that there is a region where you have the hot products always there, so that you have hot radicals and high temperature zone which can actually ignite whatever is coming, and this region should not blow out, so that is why we have this situation. So in general the high speed stream will consist of unburned mixture of air and fuel, and the low speed stream which is there in the recirculation zone will consist of hot combustion products formed with behind this flame holding recirculation zone behind the dump combustor. And you can also have a swirl stabilized combustor, where how does the recirculation zone form in a swirl combustor? Where do you see, do you know any situation where you use swirl stabilized combustors in reality? Sorry? Yeah, gas turbine engine. So there you have vortex breakdown, and there will be a central toroidal recirculation zone, and that would be what is having the pool of radicals, hot radicals, and so which has the radicals and the high temperature to initiate the combustion. So I will so therefore let me show a few typical combustion configurations, so that Derek will be happy that we are looking at practical situations. So this is like the typical dump combustor. Fluid mechanics people call it backward facing step, and the combustion people call it dump. Both are, it's like dumping into a bigger region, that is what it is. Now so this would be a dump combustor. You can also have variations of this. You can have it if you have a wall like this, let us say for example I erase this and I have a wall like this, then you have this only one side and it will break the symmetry, but typically such combustors are seen in laboratory configurations, but engineering I mean the real combustions in the field, they would be symmetric and usually would look like this. Now I will show you a variation of this. So you can have a bluff body here, and that can also stabilize the flame. Other variations which you would see are like some kind of wire or cylinder which will hold the flame in its wake, or you can see this is what is called V gutter stabilized flames, which are sometimes used in afterburners of aircraft engines. You will, these are practical combustion configurations. You can also have sorry, you can have multiple flames being stabilized on some geometry like this. That is another possibility, and they are often used in sometimes you can see it in domestic heaters. You can also have ramjet combustors which burn solid fuel ramjet, SFRJ. So they are also sometimes we use a dump. So you can have solid fuel burning and pyrolyzing here, and then we can have this vortices being formed over that. So these are, I am sure you can draw many more configurations. In fact, this paper shows both the paper shows many more configurations than this, but I have just talked about some of the configurations to give you an idea, and you can see those papers for getting. I will not speak now about swirl combustors. I will just speak about this vortex shedding and bluff body, but there also there's quite a bit of interesting instabilities that happen. So now let us take a relook at this picture in the context of these combustors, as Derek was pointing out. I will draw one side, you can draw both sides. This is adapted from the first reference, good mark and shadow. So in reality we have walls, and the walls will also interact with or flame and flow and everything, acoustics, so which is something which we cannot get rid of. Of course in the laboratory you can set up splitter plate in the wind tunnel and have flame and so on, but in real combustors you have to have walls and they will interact, and we have to worry about the interaction. So let us say we have a premixed flame coming, so we have unburned mixture of reactants coming here, and we would have some kind of vortex roll up here, and so here we have unburned reactants and there are hot combustion products here hanging around, and that is precisely the reason we have this expansion, so that this hot combustion products will be there, and they will try to get entrained into this, and there will be some kind of interface here. So this unburned mixture of reactants will try to get in this way, and the hot combustion products are trying to come in here, and then there will be interface, and then you will have a pocket of a pool of mixture which can actually burn in this vortex. Okay, so that is like a cartoon or schematic, and the exact details can change depending on how far the walls are, what is the step height and so on, but this is some kind of basic schematic of the situation that can prevail. So clearly you can see from this that the vortex structure can have a significant influence on the combustion. So in the early phase you have unburned mixture on one side and the hot combustion products on the other side, and then you do not have intense mixing and burning, but as the turbulent structures develop and the fine scale mixing happens here in the interface, you can have fine scale mixing and burning. So you have a roll up, but in reality that is not the only thing. You will have interaction between vortices because the shear layer has instability that will shed at some frequency. Those waves will have some preferred mode of excitation and so on, and then vortices will be shed, and these vortices will actually merge, and then you will probably end up having a lower frequency of the bigger organized structure, and of course this will be obstructed by the walls and severely interfered by the walls, so that the situation will be quite different from a flow from a jet. It will have some similarities, but the wall is interfering for sure, and a large interface between the fuel air mixture and the hot products will develop, and there will be fine scale turbulence and which cause entrainment, and so eventually these things and these things, adequate number of radicals will diffuse or will mix into the stream, and there will be a pool which will suddenly burn. So that will be so this phenomena will be quite periodic, and it happens cycle after cycle, and of course if you studied Rayleigh criteria which says that if heat release rate is in phase with the acoustic pressure, then you will have acoustic driving. So here there is a delay, so from here you have the mixture coming in here, coming here, and at some instant it burns very vigorously, then again this phenomenon has happened, and all the things that we studied about how the acoustic model has to be developed will again apply here, and this time delay between the fluctuations here and the heat release, that will clearly affect how the reactants are going to burn, whether they are burning in phase or out of phase, and therefore whether they are going to drive the instability or dam the instability. And people have who has researchers said that I mean this is the situation I have drawn for gas phase combustion, but even if you are having spray combustion, the spray will be entrained into the vortex, and of course situation will be much more complex because the spray will not be coming at, although if you speak to if you buy a spray, people say it has an average diameter, but average diameter is not the only thing. You have a diameter distribution, and you have all kinds of droplets, small droplets, large droplets, so it may have a average diameter, but there are small and large droplets, and the small droplets will behave in one way, they will go very well with the structure, it will almost behave like gas. The large droplet will have heavy inertia, so they would not follow the flow exactly. Similarly, if there is acoustic oscillations in the combustor, the small droplets will very well follow the acoustic oscillation. So if you have a 10 micron droplet around 300 hertz, it will fluctuate at I think 80% of the acoustic velocity, but if you have a 50 micron droplet, it will only fluctuate at 10% of the acoustic velocity. So both will be there in a typical gas turbine spray, and therefore the interaction will be very complicated, but nevertheless this plays a role, it is just that it is more difficult to study, and most of the research has been with gaseous fuels, but there is some studies on liquid droplets and so on. Now so this vortex shading typically comes under this bigger, if you talk to fluid mechanics people, they will say this is one of the large scale coherent, this is a large scale coherent structure in the flow, and this problem has to be studied along with the class of problems of shear flow instabilities in jets, wakes, and mixing layers and so on. So now I just want to give an idea of how I can get such a combustor to work. Ideally you do not want the combustor to pulse, but if you understand how it pulses, then it may be a possibility, there may be a possibility to make it not pulse. So let us this is a design which is often used in tunable pulse combustors. So you can make a pulse combustor and you can make it pulse at any length. So so what you can do is, if you can move this bluff body back and forth, so as you come close the velocity here will increase, as you push the bluff body forward the velocity here will decrease, and typically these things are shared at there will be certain Strouhal number modes, which means the Strouhal number will be constant at some number, and so which means if you increase the velocity, the frequency of shading will increase. So if you pull it back, the frequency will go up, if you push it forward the frequency will come down. So if your frequency is going up and coming towards this frequency of the acoustic oscillations in the duct, that is if you have certain preferred duct frequencies, the natural modes, and then you are coming towards that, and then this vortex shading will suddenly lock to the acoustic oscillations, and then this instability can happen. But if you are going away, then the chances of these things coming closer are, it does not have to exactly match some, I mean these are nonlinear phenomena, so you just have to come close, and then if you are going away, if the both frequencies are going away from each other, then you are actually detuning the system, or you are actually making you will not have oscillations. Same kind of thing happens here. Here you can't tune at a given velocity, but at certain velocities the vortex shading frequency may come close to the frequency of the combustor, and then both will lock to each other. So that is how in a crude sense or in an intuitive sense you can understand the instability mechanisms. So here if you want to remove the instability, you will have to, if there is instability at some flow configuration, you can change the inlet area and change the speed, and therefore you will change the frequency of the hydrodynamic instabilities away from, you can make it go away from the acoustic oscillations. So this is some intuitive explanation of how pulse combustor of this or a combustor of this sort pulses. Yeah, first in 70s people or 60s 70s people came up with models for fluid mechanically how this coherent structures appear and all that, and now there are calculations. So you calculate for all these things. So you have a CFD model for all these things, which now you couple, or you can have a full compressible solver which will capture everything if you are rich and you have big computers and fast computers. But if you don't, you can actually solve for the hydrodynamics separately, and you can have some asymptotic expansion and then input this into the acoustic solver and do a coupled solution. So people have solved for it. So the concept of large scale structures were first advocated by Brown and Roscoe. Roscoe 1974. JFM is Journal of Fluid Mechanics, volume 64, page 775 to 816. There is also another very nice article about the review articles of this whole concept, Ho and Hoyre, Patrick Hoyre, in Annual Review of Fluid Mechanics, volume 16. This is also a very prestigious journal. You can't just send articles, they will have to invite you. So if you are a big shot, very acclaimed person in the area, then you will get an invitation to write an article in Annual Review of Fluid Mechanics. And again, this is like the earlier journal I said, this has only review articles and no regular articles. And so when a subject reaches a certain level of maturity, the big shot in the subject will be asked to write a review article, and this is a review article about this concept of coherent structures. So based on laboratory experiments with low Reynolds number, so this is fluid mechanics experiment, not really combustion, low Reynolds number experiments of turbulent flow, it was shown that the shear layer initially develops instability waves in the initial region, and then these waves reach a certain energy level, they roll up into vortices, and so there will be an initial vortex shedding frequency, let's call it Fi, which is also the most amplified frequency, and it is often determined by characteristics such that of the velocity profile, shape of the velocity profile, turbulence in the profile, initial shear layer momentum thickness, and the jet exit velocity. And so let's draw this concept. So you will have this instability waves, and they will start rolling up. And initially there will be a Fi, okay, and so this Fi will depend on Fi is initial vortex shedding frequency at the initial region, so that will depend on the Fi is the most amplified frequency. So it depends on the characteristics of the exit velocity profile, that is the velocity profile here. And those would be, let's say, the shape, the turbulence levels there, theta naught, the initial momentum thickness, also of course u naught, the jet exit velocity. So we can always look for scaling, just like we have non-dimensional number like Reynolds number to look at how viscous forces scale. So similarly you can also have a Strouhal number which number denoted by St. So Sti equal to Fi theta naught over E naught, and typically people have done linear stability theory and found that from linear stability theory Sti equal to 0.017, and the reference would be Michel K. JFM more 23. So typically JFM has thorough articles which are quite long. You do not see a 2-page article in JFM, you see 20-page article or 40 or 50-page articles in JFM, which will give comprehensive treatment. So let us indicate this in our picture here. So this Sti equal to Fi theta naught over U naught equal to 0.017. Now the initial vortices, many will be shed, but they grow and they merge and are convected downstream. So vortices merge, grow and are convected downstream. So you can imagine that when you have vortex merging, what happens to the frequency? Will it come down or will it increase?
It actually depends upon whether they are merging in phase or.
Let's say they are merging.
In phase means it will come down.
Yeah, I mean if you have 10 vortices and they merged into one vortex, then naturally whatever happens they merge, it will come down, right? So the frequency will come down. So due to merging and entrainment, the shear layer will also start spreading, and the because when this happens, it is going to entrain air from the surroundings, and then this vortex structure is going to get big, and the vortices are merging, so that also makes it big, and the frequency associated with the dominant large vortices decreases. Okay. So in the shear layer of a jet, several vortex interaction can occur before the initial separation of the shear layer and end of the jet potential core. So let me write this. So due to merging and entrainment, the shear layer spreads and the frequency of this larger vortices how they will decrease. So so the shear layer will therefore be characterized by several instability frequencies associated with different sizes of the vortices, and the region at the end of the potential core, by then all this would have merged to a big vortex, and that is governed by what is called the jet column instability, and the vortex fluctuations in this region will have another characteristic frequency which we will denote as Fj. Let us say if this is the end of potential core, so let us say here we will have some frequency Fj, which is typically the second or the third subharmonic of the initial shear layer frequency. You will have a certain frequency Fi, this would be Fj would be Fi divided by 3 or something like that typically. And this frequency scales with some other variables. So Stj is the this frequency which is at the, you see at the end of the potential core, and it scales with the diameter of the jet and u naught, the exit velocity of the jet, and typically you see in the ratio of 0.25 to 0.5, that is the Stj in this ratio. So you start off with Fi and you end up with the Fj, and Fi scales with momentum thickness and the mean velocity of the exit of the jet, whereas Fj actually scales as Stj equal to Fj du over u naught. So if you look from a combustion point of view, we want mixing either between fuel and air, or we want to promote mixing between the hot gases and the cold gases, and that is when our combustion will happen. So the large scale structures will be beneficial for the they are beneficial for the enhancement of large scale mixing or bulk mixing, that is you take this fluid and mix with that fluid, but nevertheless it may not really enhance fine scale mixing or molecular mixing, and only if mixing happens in the molecular level you will have combustion, otherwise you still have big pockets of fuel and big pockets of air, and that is not enough. You have to have mixing in the small scale. So in the presence of large scale structures, so we need to transition to fine scale mixing, and that is often initiated by the braids of vortices where high strain rates between the high and low speed streams exist, that is here, okay, in this braids. However, the initial fine scale turbulence is limited only to this region, but it is conjectured that fine scale turbulence is abruptly enhanced during the roll up of vortices. When the vortex is rolling up, suddenly this fine scale turbulence increases, and therefore fine scale mixing increases, and therefore this suddenly causes the reaction to occur, and this is a periodic phenomenon. The two Strouhal numbers, and if you see a spectrum of a jet, the noise, it will have many frequencies, it is not just one particular thing. So you will have a frequency associated with in the initial layer and a frequency at the other layer, and you will see actually a kind of broad band spectrum, but with some preferred frequency. You will still see a prominent spectrum there, a prominent peak there. So you will see a lot of frequencies, but some frequencies will be preferred.
So like where do we use Strouhal number, like a particular Strouhal number means more mixing or?
You can't quite say that. Strouhal number means it is about receptivity. So if you are forcing the if you want to force with acoustic oscillations, so if you force at this frequency, then you are actually you have a coherent structures coming, and there is a preferred frequency at this Stj, and if you send the acoustic wave corresponding to that, you will get this coherent structure will get very organized, and you will get a, now if you look at the spectra you will get a very sharp peak. If you are exciting here, you are amplifying the waves here. So it's about receptivity actually, not just mixing. So, and once you have the coherent structure, it leads to this bulk mixing, and then if the high strain rate available, then which happens during roll up, then you can have this fine scale mixing and combustion. So that's why it doesn't really start burning right from the beginning. It just gets in, and then it rolls up, and then it bang, it burns, and then again the same thing happens. So it happens in a periodic way. People are taken high speed movies and have seen this. So does it answer your question? So it's about getting the like this guy responds to certain frequencies, he has certain preferred frequencies, so if you excite in those preferred frequencies he will respond.
So can we say Fj is greater than Fi or Fi is greater than Fj?
Yeah, Fi is greater than Fj.
Then how is this Prabha number Sti less than St then?
Because this is non-dimensionalized with theta naught, which is very small, that is the momentum thickness. Here it is with d, which is the sorry. So theta naught is the like the momentum thickness. Everybody know what is the momentum thickness? Okay. So this is the jet diameter. So
Just by definition, right?
just by definition. So if you define that way, this is the way it scales. So if you do experiments with several different diameter jets, then it's and then you collapse all your frequencies, all your data will merge if you non-dimensionalize this way and not any other way. Here this frequency will collapse in different experiments if you non-dimensionalize with momentum thickness.
Somewhat similar to Reynolds boundary layer Reynolds number and free stream Reynolds number. We use two different lengths.
Yeah, something like that. Correct. So here we use different time scales.
Yeah, different theta and d.
Yeah. This is f divided by you can rewrite this as f divided by u over theta. So f is like 1 over time scale, this is another 1 over time scale. Okay. Any other questions? Okay, so I think it's a good place to stop.